welcome to Civil Engineering Edge. Today, we're diving into an exciting blend of creativity and science, building a bridge from Legos to test how it stands up against earthquake forces. Civil engineers spend years studying how to design structures that can survive powerful ground motions, and today, we'll explore those same principles on a smaller, more playful scale. Using colorful Lego bricks, we lines model how real bridges behave during seismic vibrations and discover the secrets behind making them earthquake resistant. Stay tuned till the end to see if our Lego bridge can survive the shaking test. Introduction and inspiration. Bridges are among the most vital infrastructures in our modern world, connecting cities, supporting transportation networks, and enabling economic growth. However, they're also some of the most vulnerable structures during natural disasters, especially earthquakes. Engineers constantly innovate to ensure that bridges remain safe, flexible, and durable under such unpredictable conditions. In this experiment, we take inspiration from those real-world engineering marvels and translate them into a fun, hands-on learning experience using Legos. LEGOs are not just toys, they're an incredible educational tool that helps visualize and test complex engineering concepts in a simple, interactive way. By building a bridge entirely out of Lego bricks, we can simulate various structural responses, bending, vibration, and failure patterns, just like in real-life engineering labs. The beauty of this experiment lies in its simplicity. Anyone, from students to aspiring civil engineers, can grasp how materials, connections, and supports influence a bridge's strength. Through this playful yet scientific approach, we'll discover how engineers use smart design strategies like base isolation, flexible joints, and energy dissipation systems to make structures earthquake resistant. This project not only sparks creativity, but also deepens our appreciation for the field of structural engineering, where imagination meets precision to protect lives and cities. Introduce the concept of earthquake-resistant design and its importance. Earthquake-resistant design is one of the most crucial aspects of modern civil engineering. It focuses on creating buildings and bridges that can absorb and withstand the intense shaking forces generated during an earthquake. Instead of resisting movement completely, these structures are designed to flex and adapt without collapsing. This flexibility helps reduce damage and saves lives. The key principle is understanding how seismic waves transfer energy through the ground and into the structure. Engineers incorporate smart design features such as damping systems, flexible foundations, and strong reinforcement to control the movement and distribution of forces. The goal is to make structures completely immune to earthquakes. That's impossible, but to ensure they remain safe and functional even after significant tremors. By designing for controlled deformation and balanced load paths, engineers ensure that bridges and buildings don't fail suddenly. This field combines physics, material science, and creativity, all working together to make the built environment more resilient. Earthquake-resistant design stands as a testament to how engineering can protect human life and preserve critical infrastructure in the face of nature's power. Briefly discuss the devastation caused by earthquakes and the need for robust structures. Earthquakes are among nature's most destructive forces, capable of reducing entire cities to rubble within seconds. Over the decades, powerful earthquakes in Japan, Nepal, Turkey, and India have shown how devastating seismic events can be when structures aren't built to endure them. Bridges collapse, highways crack open, and essential services are disrupted, leading to massive economic losses and tragic loss of life. When a bridge or building lacks proper reinforcement or flexibility, the intense vibrations from an earthquake cause structural failure. The shaking generates lateral forces that pull and push materials beyond their elastic limits, causing columns to buckle and joints to snap. Once a critical section fails, the entire structure can collapse like a domino chain. This is why earthquake-resistant design is not optional, it's essential. Engineers must consider seismic loads right from the design phase, using specialized techniques such as flexible joints, deep foundations, and energy-absorbing materials. These innovations ensure that structures can sway, dissipate energy, and maintain integrity even during extreme shaking. Investing in robust structural design saves countless lives and prevents catastrophic destruction, turning engineering into a guardian of safety against nature's unpredictability. Highlight the fun and engaging approach of using Legos to demonstrate these principles. Using Legos to demonstrate earthquake-resistant bridge design brings science to life in the most enjoyable way possible. These colorful building blocks allow us to visually and physically explore engineering principles, from load distribution to vibration damping, without needing expensive lab equipment. With Legos, we can easily modify the structure, test different support systems, and observe how design changes affect stability. In our experiment, we simulate an earthquake by shaking the surface beneath our Lego bridge and watch how it responds. Does it twist, crack, or stay intact? By experimenting with different configurations, like adding base isolators or strengthening the piers, we see how small design changes make a big difference. This hands-on method helps students and enthusiasts grasp abstract engineering concepts more clearly. It transforms learning into discovery, allowing you to witness the real impact of engineering decisions. Most importantly, it fosters creativity, the heart of all great innovations. Through this Lego Bridge Challenge, we celebrate the spirit of engineering, solving serious real-world problems through curiosity, imagination, and practical experimentation. Who knew building with toys could teach us so much about saving lives and constructing safer, smarter structures? Bridge construction and design. Designing and constructing a bridge, even from Lego bricks, requires a deep understanding of how forces act on a structure. The goal isn't just to make something that looks good, but to build a model that behaves realistically under stress. In our case, the focus is on earthquake resistance. Before assembling the Lego bridge, we carefully plan its layout, span length, and support system. The bridge must distribute loads evenly while allowing flexibility during shaking. Engineers follow the same process in real life, analyzing stresses, designing supports, and selecting materials that can absorb energy during seismic events. In our Lego version, every brick placement represents a structural decision, from choosing the right base width to adding cross bracing between piers. The bridge's deck must remain stable, and its supports must flex slightly instead of breaking. We'll also introduce innovative techniques inspired by real engineering, like base isolation pads and shock-absorbing joints made from flexible Lego pieces. This combination of creativity and engineering precision makes the process both educational and exciting. Through this model, we not only learn how bridges are designed, but also gain a hands-on understanding of how careful construction decisions make the difference between collapse and resilience during an earthquake. Showcase the building process of the Lego bridge, emphasizing design considerations for seismic resistance. The Lego bridge building process begins with a clear design plan focused on stability and flexibility. First, we create a strong foundation using wide, interlocked Lego plates that act as the base. This base spreads out seismic forces evenly during shaking. Next, we construct the bridge piers, the vertical supports, ensuring they are sturdy yet capable of minor movement to absorb vibrations. For the bridge deck, Lego beams are laid out to form a continuous span between supports. We reinforce this deck with diagonal bracing underneath, which mimics the role of trusses in real bridges. This triangular arrangement helps distribute loads efficiently and prevents twisting or buckling. To make our model earthquake resistant, we experiment with flexible connections where the deck meets the piers. By slightly loosening these joints or using rounded pieces, we allow controlled movement, a simple representation of base isolation systems used in modern engineering. Finally, the bridge is anchored on a simulated earthquake platform that will test its durability. This thoughtful approach transforms a simple Lego project into a realistic engineering demonstration, showing how small design choices can dramatically improve a structure's ability to withstand seismic forces. Explain the principles of structural engineering applied in the bridge design, including triangular bracing, flexible joints, and base isolation concepts. Our Lego bridge may look simple, but it embodies several key principles of structural engineering. The first is triangular bracing, one of the oldest and most effective methods for stabilizing a structure. Triangles distribute forces evenly through their sides, preventing distortion under stress. By adding diagonal braces beneath the bridge deck, we make it more rigid and able to resist bending or twisting during shaking. Next, we apply flexible joints, the secret to resilience. In real-world engineering, flexible connections allow controlled motion between components, reducing stress concentration. In our Lego model, we replicate this by slightly separating the deck from the piers or using pivot-like connections. This flexibility lets the bridge absorb motion instead of snapping under pressure. Finally, we simulate base isolation, where the structure's foundation is separated from the ground using flexible pads. These pads reduce the transfer of seismic energy upward. Our Lego version uses soft materials or movable plates beneath the supports to mimic this effect. Together, these three design strategies of bracing, flexibility, and isolation demonstrate how civil engineers use smart mechanics to make bridges safer and more durable in earthquake-prone regions. Discuss the importance of choosing strong materials and ensuring proper connections for stability. In both real-world construction and Lego modeling, the strength of materials and quality of connections determine whether a structure stands or collapses. Earthquake resistance depends not only on design, but also on how well each element is bonded and how materials behave under stress. In our Lego bridge, each brick must interlock tightly with its neighbors to create a continuous load path. Loose or weak connections can easily come apart during shaking, mimicking how poorly joined components in real bridges can fail under seismic stress. Engineers call this structural integrity, the ability of a structure to act as one cohesive unit. Material selection is equally vital. While our Lego bricks are made of plastic, they symbolize the use of strong, ductile materials like reinforced concrete or steel in real bridges. Ductility allows materials to stretch and deform without breaking, absorbing energy during earthquakes. Proper connections, such as well-fitted joints, anchor bolts, and reinforcements, help maintain stability and prevent collapse. Even in this small-scale model, we learn an important lesson. Great design is only effective when supported by quality materials and precise construction. Every connection counts, and every material choice contributes to safety and longevity, testing, and results. After constructing our Lego bridge, it's time to put our design to the ultimate test, a simulated earthquake. This stage is where theory meets reality, and every design decision comes into play. To replicate seismic activity, we'll use a shaking platform that mimics ground motion during an earthquake. As the table vibrates, we'll observe how the bridge reacts, whether it sways, bends, or begins to crack. This test helps us visualize the forces that act on real bridges during earthquakes and how design elements like triangular bracing, flexible joints, and base isolation perform in practice. By observing how the Lego bridge transfers and dissipates energy, we can evaluate its overall stability and resilience. The most exciting part of this process is experimentation. We lines test different versions, some with reinforcements and some without, to see how each handles the same level of shaking. Through this comparison, we'll gain valuable insights into how engineers refine and strengthen real structures. This small-scale experiment vividly demonstrates that even simple materials, when properly designed, can withstand significant motion, proving that good engineering is about smart design, not just strong materials. Demonstrate the earthquake simulation using a shaking table or a similar setup. To simulate an earthquake, we place the completed Lego bridge onto a shaking table, a device that mimics ground vibrations. The table can move back and forth at adjustable speeds, representing the horizontal forces that occur during real seismic activity. In professional engineering labs, large-scale shaking tables test actual bridge and building models to analyze their behavior under controlled seismic conditions. For our demonstration, we'll use a smaller setup, a platform mounted on springs or rollers, moved manually or with a motor. As the shaking begins, we'll record the bridge's movement using slow-motion video to capture even the smallest shifts. The vibrations will start gently, simulating minor tremors, and gradually intensify to represent stronger quakes. We lines pay close attention to how different parts of the bridge respond, whether the deck vibrates uniformly, if the piers flex as intended, and how well the base isolation pads absorb energy. This setup allows us to clearly visualize the real-time interaction between structural design and seismic motion. It is an exciting and educational way to see engineering principles come alive, proving that understanding structure behavior is just as critical as building it. Analyze the bridge's performance during the simulated earthquake, focusing on its ability to withstand shaking and maintain its structural integrity. As the simulated earthquake begins, the Lego bridge starts to sway, a natural response to lateral ground motion. Our first observation is how the structure flexes without immediately cracking or collapsing, which indicates that the design's flexibility works effectively. The triangular bracing beneath the deck helps maintain alignment, minimizing twisting and spreading the forces evenly throughout the bridge. The flexible joints perform exceptionally well by allowing slight movement between the deck and the piers, reducing stress concentration at the connections. Meanwhile, the base isolation system, made from soft Lego plates or movable supports, dampens vibrations and prevents excessive transfer of energy from the shaking platform to the superstructure. Throughout the test, we observe minor shifts but no significant failure, meaning the structure retains its integrity under continuous shaking. This behavior mirrors how real earthquake-resistant bridges perform during moderate seismic events. They move, absorb energy, and then return to stability. By analyzing the recorded footage, we can identify which sections experience the most stress and where reinforcements might be needed. The experiment successfully demonstrates that a well-balanced design combining strength, flexibility, and energy absorption can significantly improve earthquake performance. Compare the results with different designs and materials, highlighting the effectiveness of earthquake-resistant features. After testing our primary Lego bridge, we construct a few alternative models to compare performance. The first version uses a rigid, non-flexible design without bracing or isolation pads. During shaking, this version quickly fractures at its joints and loses balance, clearly showing the weakness of inflexible structures. Next, we test a reinforced design that includes diagonal bracing but no flexible joints. This model performs better, resisting some lateral forces, but the rigid deck connections still lead to partial cracking under strong vibrations. Finally, our earthquake-resistant model, equipped with triangular bracing, flexible joints, and base isolation, performs best. It sways during the shaking but remains intact, successfully absorbing and redistributing energy. These comparative tests highlight how each earthquake-resistant feature contributes uniquely to stability. Bracing adds stiffness, joints offer flexibility, and isolation pads reduce energy transfer. Together, they form a holistic defense system that minimizes damage. The experiment proves a crucial engineering lesson. Resilience comes from smart design, not just material strength. Even with simple Lego bricks, we can observe the same mechanical behaviors that govern real bridges, showing how thoughtful design transforms vulnerability into durability. Lessons learned and applications. Our Lego bridge experiment has been a fascinating journey into the world of earthquake-resistant design. Beyond the fun of building with colorful blocks, this activity gave us a real understanding of how civil engineers approach one of the world's toughest challenges: designing structures that can survive the unpredictable power of earthquakes. From the experiment, we learned that flexibility, proper load distribution, and strong connections are key to a structure's survival. Bracing, damping, and base isolation are not just textbook ideas. They're practical tools that protect lives and infrastructure. Watching our Lego bridge endure shaking helps us appreciate the science and creativity behind real bridges and skyscrapers. These lessons go far beyond the classroom. They show that engineering is not only about calculations, but also about imagination, testing, and improvement. Each failed model teaches something new about how structures behave and how to make them safer. The experiment proves that innovation often starts with curiosity, even with something as simple as Lego bricks, and ends with real-world solutions that build safer, more resilient communities. Summarize the key takeaways from the Lego bridge experiment, emphasizing the importance of understanding structural principles and implementing them in real-world constructions. The Lego bridge experiment revealed how deeply interconnected design, materials, and forces are in structural engineering. We observed that structures designed to flex and distribute loads effectively can endure far greater stress than rigid ones. Triangular bracing, flexible joints, and base isolation systems emerged as the most important features for maintaining balance and stability during an earthquake. One of the most valuable takeaways was the realization that every connection matters. Even small weaknesses in joints can lead to large-scale failure when subjected to vibrations. Conversely, small design improvements can greatly enhance resilience. The Lego model clearly demonstrated that good engineering isn't just about strength. It's about smart design and adaptability. In real-world construction, these same principles are applied on a larger scale. Civil engineers use steel reinforcements, shock absorbers, and flexible foundations to create structures that sway safely without collapsing. This experiment not only simplified complex engineering concepts, but also emphasized the importance of testing and iteration, the continuous process of refining designs until they achieve maximum safety and performance. Understanding these principles helps future engineers bridge the gap between classroom learning and real-world problem-solving. Discuss the practical applications of earthquake-resistant design in buildings, bridges, and other infrastructure projects. Earthquake-resistant design plays a vital role in protecting lives and preserving infrastructure in seismically active regions. In buildings, engineers use shear walls, damping devices, and flexible foundations to absorb and redistribute earthquake energy. Skyscrapers are designed to sway instead of breaking, ensuring occupants remain safe even during strong tremors. In bridges, earthquake-resistant principles are applied through base isolation bearings, flexible joints, and shock-absorbing expansion devices. These systems allow the bridge deck to move independently of the supports, minimizing stress concentrations and preventing collapse. Reinforced concrete and steel girders are strategically placed to handle both vertical and lateral loads efficiently. Other critical infrastructures, such as hospitals, power plants, and transportation hubs, also rely on seismic design innovations. Engineers use vibration control systems and advanced materials that maintain functionality even after an earthquake. These practical applications prove that understanding seismic behavior is essential for sustainable development and disaster resilience. Ultimately, earthquake-resistant design transforms vulnerability into preparedness. By combining scientific principles with innovative technology, engineers create safer, smarter structures that can stand firm against nature's unpredictable forces, ensuring communities recover faster and lives are protected. Encourage viewers to explore the field of structural engineering and the role of innovative solutions in disaster preparedness. Structural engineering is more than designing buildings. It's about safeguarding lives through innovation and creativity. The Lego Bridge experiment offers just a glimpse into the fascinating world of civil and structural engineering, where every decision impacts how a structure responds to real-world challenges like earthquakes, wind, and floods. By exploring this field, you can become part of a profession that blends science, design, and problem-solving to make our world safer and more resilient. Engineers today use computer simulations, smart materials, and AI-based monitoring systems to predict and prevent failures before they occur. The possibilities for innovation are endless. Disaster preparedness begins long before a disaster strikes. It starts with smart design and responsible engineering. Whether you're a student, educator, or curious learner, experimenting with models like our Lego Bridge is a great way to understand the basics and spark new ideas. So, keep experimenting, keep asking what if, and remember, every great engineer started by being curious. By embracing creative thinking and engineering knowledge, you can contribute to building a future where structures don't just stand tall but stand strong against the forces of nature. Call to action and next steps. Now that you've seen how a simple Lego bridge can demonstrate powerful engineering principles, it's your turn to get creative. Engineering isn't just about studying formulas. It's about experimenting, observing, and learning through real-world simulations. Using everyday materials like Lego bricks, you can explore how structures behave under stress and discover how smart design leads to safety and stability. This project encourages you to think like an engineer, plan, build, test, and improve. Try different bridge shapes, change the supports, or add bracing to see what works best. Every experiment teaches something new about how energy moves through structures during earthquakes. As you build and test, remember that these small models represent big ideas used in real-life infrastructure, from earthquake-proof skyscrapers to resilient bridges. Engineering curiosity today becomes innovation tomorrow. So, pick up those Lego bricks, challenge your creativity, and let's continue building a safer world together. Encourage viewers to try building their own Lego bridges and experiment with earthquake-resistant design principles. If you enjoyed this experiment, it's time to take the next step. Build your own Lego bridge and put it to the test. Start simple. Create a small span using standard Lego bricks and test how it reacts to shaking. Then, gradually improve your design by adding triangular bracing, flexible joints, or even base isolators made from soft materials like rubber bands or foam pads. Try varying the length of the bridge or changing the type of supports to see how it affects performance. Record your tests, analyze the results, and share them with friends or classmates. You'll be amazed at how small design changes can dramatically improve stability. This hands-on approach isn't just fun, it's educational. You'll understand how real engineers think, design, and solve problems. By experimenting with your own Lego bridges, you'll gain insight into the fascinating world of earthquake engineering while developing critical thinking and creativity. So grab your Lego set, find a flat surface, and start building. Let's see if your bridge can survive the shake test. Provide resources for further learning about earthquake preparedness and structural engineering. If today's experiment sparked your curiosity, there are plenty of ways to learn more about earthquake engineering and preparedness. Start with online platforms like National Geographic Education, Ready, Gov, or USGS Earthquake Hazards Program. which offer interactive tools and videos explaining how earthquakes occur and how we can prepare for them. For those interested in structural design, explore mid-open courseware, NPTEL civil engineering lectures, or Coursera courses on structural dynamics and seismic design, all free and beginner-friendly. You can also visit the websites of professional bodies like the American Society of Civil Engineers ASCE or the Earthquake Engineering Research Institute TERI for real case studies and project insights. Books such as Design of Earthquake-Resistant Structures by Dowrick or Seismic Design for Architects by Andrew Charlson are great starting points for deeper understanding. Remember, knowledge is the foundation of safety. Whether you're a student, hobbyist, or aspiring engineer, learning how to design safer structures is a step toward making the world more resilient against natural disasters. Keep exploring, keep questioning, and keep building. Every bit of learning brings us closer to stronger, safer communities. Leave viewers with a sense of wonder and inspiration to make a positive impact by promoting knowledge and preparedness. As we conclude, take a moment to appreciate what this small Lego experiment represents: the power of human creativity, curiosity, and problem solving. Behind every earthquake-resistant building or bridge lies a story of innovation, teamwork, and determination to protect lives. And it all begins with learning and imagination. Even the simplest models can inspire life-changing ideas. Today, it might be Lego bricks. Tomorrow, it could be advanced materials, AI sensors, or smart city designs that reshape how we build. The next great engineer, researcher, or innovator could be you. Our world needs thinkers and builders who not only design strong structures, but also build stronger futures, communities ready for the challenges of nature. By understanding, preparing, and innovating, you can make a lasting difference. So stay inspired, stay curious, and keep learning. Share your experiments, your discoveries, and your passion for engineering with others. Because when knowledge spreads, safety grows, and that's how we build a brighter, safer, and more resilient tomorrow. Together, let's keep turning imagination into innovation. One Lego brick, one bridge, and one brilliant idea at a time. Conclusions and benefits. Through this engaging experiment, we've discovered how a simple Lego model can teach powerful lessons about structural behavior and earthquake engineering. The project clearly demonstrates that even small-scale models can mirror the fundamental principles that protect real structures from collapse during seismic events. By integrating features like triangular bracing, flexible joints, and base isolation, we saw how design decisions directly influence a structure's ability to resist shaking and remain stable. One major conclusion is that strength alone is not enough. Resilience comes from adaptability. The most effective structures are those designed to move with the earth, not against it. This principle applies equally to bridges, skyscrapers, and residential buildings. Our Lego bridge showed that flexibility, proper load distribution, and well-connected components work together to prevent catastrophic failure. The benefits of this hands-on experiment go beyond structural understanding. It encourages critical thinking, creativity, and problem-solving, essential skills for every aspiring engineer. By experimenting, testing, and improving designs, learners gain real insight into how engineers approach complex challenges in the real world. Ultimately, this activity combines fun and education to foster curiosity and inspire future innovators. It reminds us that engineering is not just about construction. It is about creating solutions that save lives and strengthen communities. Thank you for joining us on this exciting journey into the world of earthquake-resistant engineering. Through our Lego Bridge Challenge, we've learned how simple ideas can lead to powerful understanding and how imagination fuels innovation. If you enjoyed this experiment, don't forget to like, share, and subscribe to Civil Engineering Edge for more creative, educational projects that bring engineering concepts to life. Stay tuned for our next video, where we'll explore another fascinating topic from the world of civil engineering. Until then, keep building, keep learning, and keep shaping the structures of tomorrow.